Okay, now we should be live. Let me just check one more time and make sure audio is working. And can I see my hand? Okay, that all looks good. Let me unplug this set of headphones and let's get started. Okay, so the agenda for today is to just do some practice with the stuff we covered last time, and if we cover it fast enough, then we might get into the next unit, which is perfectly fine, except the only thing that really bothers me about it is having to split the stream into parts after it's done. I think I like it better when each stream is kind of self-contained and restricted to one individual unit, but we'll see. We'll see how I'm gonna organize that. I'm probably just gonna go with the flow and cover whatever I get to when I get to it, and that'll be that. Let me get my pens out. Just, leave them on the desk over there. Okay, so I don't even think I should be on this screen right now. Last time we just discussed the topic of vectors, and we introduced what they were, how they differ from scalars, all that good stuff. Then we spent some time on the topic of vector addition and subtraction, mostly addition because subtraction is just adding the negative of a vector. And we wrapped up with an example of a vector addition and a discussion of the three types of multiplication that can be done with vectors. So I did assign some homework, which you can see in the course plan. Do I even have that linked in the description of this stream? If it's not in there, then you should be able to find it in the description of the previous stream. I'll have to double check that afterwards, but if you just go to my website, althetutor.com/physics1 course plan, all lowercase, you'll be able to find it just fine. Anyway, let's go ahead and actually open up the homework assignment. So let me switch to this screen, and we had for practice, we had vector addition in 2 dimensions, vector decomposition practice, vector addition with scalar multiplication and displacement, which I didn't really cover an example of last time, but you probably have enough information to go off of to have been able to do that. But if you struggled with it, that's okay. We're gonna go over how that assignment is done. And then we've got the math essentials for physics. I already have the solution videos for 4 of them, if I'm not mistaken, so I'll just go over, for the most part, the 2 that I never recorded solution videos for. So without further ado, let's get started. Vector addition in 2 dimensions, exercise 2 only. Oh yeah, exercise 1 is just like an overview of physics, so yeah, we don't need that. I mean, you're welcome to try it out if you want. But anyway, a really simple question. It says, for the following scenarios, find the sum of the vectors and remember to use SOHCAHTOA and Pythagorean theorem as needed. A box is being pulled towards the east direction with a force of 5 newtons. We will go over what newtons are when we get to the force chapter. At the same time, it's being pushed toward the south direction with a force of 12 newtons. And all we have to do is figure out the resultant force, the vector sum of those 2 forces. So let me go ahead and I don't really need the box itself. What I've got is 2 vectors, and I want to add them tail to tip, or tip to tail, however you want to say it. So they're drawn in the diagram tail to tail, which I guess we can go over this because we didn't go over it last time. So that's a 5 Newton force to the east and a 12 Newton force to the south. I guess we can go over how you would add vectors if you were connecting them tail to tail instead, because there is a method that you can use for this. So if you connect them tail to tip. Oh great, is the green marker already giving up on me? Or did I call it a marker? Pen. If I draw the first vector and then at its tip I start the next vector, then I form a triangle, and in this case a very special triangle, a right triangle. So this is sometimes called the triangle rule of vector addition. Wow, all my pens are acting up today. What happened? If you try to form the resultant of two vectors by connecting them tail to tip, then yeah, you get a triangle. This only works if you're strictly adding two vectors. If you're adding three or more, then you're going to get something less fancy looking, not guaranteed to be very nice, recognizable geometric shapes. But the other thing you can do is you can connect the two vectors you're trying to add tail to tail, and then you can draw copies of them to make, well, in this case, because they're at a right angle to each other, they form a rectangle. But if I was adding two vectors that were not at right angles to each other, like say these two vectors, and I wanted to draw copies of them, then normally what I would form is a parallelogram, which is why this is sometimes called the parallelogram rule of addition, and the sum is just going to end up being the length of the diagonal of this parallelogram. So if this is A and that's B, then this blue vector over here is A plus B. And then the opposite diagonal would be, I don't see any special relationship there, but I seem to remember something about the opposite diagonal being the other diagonal, this, having some sort of special meaning, but I'm blanking on what it is right now. I'm probably going to facepalm after this stream once I realize, because it's probably going to end up being something super trivial, but anyway, if you hear your teacher referring to the parallelogram rule, then this is what they're talking about, connecting a pair of vectors tail to tail instead and completing a parallelogram, or in this specific case, a rectangle. Either way, you end up with the same lengths. You still end up with a right triangle between your resultant vector and one of your starting vectors, and then the copy of the other vector. Those still form a right triangle. We're just going to stick to this. But yeah, that's your little detour triangle rule and parallelogram rule. If you hear those terms being used, that's what your teacher is referring to. Anyway, a simple Pythagorean theorem here. That's a right triangle. So we can do 5 squared plus 12 squared, 25 plus 144 equals the length of the resultant squared. So that's 169, which is equal to 13 squared. Yeah, this is one of those special right triangles where the numbers are all nice and you don't have any ugly decimals to deal with. Oh no! I just realized I just realized that whole time I was drawing, it was still stuck on that other screen. Man, I need to get better at realizing when I'm doing that. I need to double check my streaming software more often. Okay, recap. So I drew this first, connecting them tail to tail. Then I drew this for the triangle rule, connecting them tail to tip as I showed last time. And there's a parallelogram that I drew with the angle between the two vectors not being 90 degrees as it was here, just to emphasize why the resulting shape is a parallelogram. You start with your two vectors connected tail to tail. I'm sorry that I have to repeat this, but it is what it is. You start with them connecting tail to tail, and then you draw copies of them, and then connect the place where the two tails intersect to the place where the tips of the two copies intersect. In other words, the diagonal of this parallelogram, and that is your vector sum right there. So that's the parallelogram rule. Triangle rule is just what we did last time. Connect them tail to tip. They form a triangle, as long as you're just using two vectors being added or subtracted for that matter. Okay, so going back to the main problem at hand, we've got sides of 5 and 12 making a right angle with each other. We can do Pythagorean theorem to figure out the length of this pink side, and we get 13 for the length. So this thing has a magnitude of 13 in the same units, so newtons. And now we need to figure out the angle. So I'm just going to use, let's see, the opposite to this angle is 12. I'll call this angle theta. The opposite to this angle is 12. The adjacent is 5. So opposite over adjacent would be 12 over 5. Would be equal to the tangent of theta. If I take the inverse tangent of 12 over 5, then I will get theta. Inverse tangent of 12 over 5. I get about 67.4 degrees. So I'm getting theta. I guess I'll draw an arrow to it like that. Theta equals about 67.4 degrees. And this would be, let's see, starting from the eastward direction, I go 67.4 degrees towards the south. So that would be 67.4 degrees south of east. So I would say the resultant is 13 newtons at 67.4 degrees south of east. Final answer. Okay. Now we move on to part B, which says a bottle rocket is moving to the right with a rocket propulsion force of 8 newtons. Gravity pulls it toward the ground with a force of 6 newtons. Pretty much the same idea. I don't think you need to see me working this one out. They're basically the same two directions again, one to the right and one down. You've got, whoops, that's not very straight. You've got 8 newtons to the right, and I'm going to connect to the tip of that my 6 newtons down. And the resultant will be 6 squared plus 8 squared is 36 plus 64 is 100, which is 10 squared, so that's going to be 10 newtons. And the angle over here is going to be, what was it, 36.9 is what we got last time? 36.9 degrees. Let me check. Inverse tangent of 6 over 8. Whoops, syntax error. Oh, yeah, about 36.9 degrees. And this one would be, well, we don't know if this bottle rocket is headed north or east or south or west. We've just got vertical and horizontal directions, so I would just call this 36.9 degrees below horizontal for the total force. Okay, so that was the first assignment. Second assignment was just practicing with vector decomposition. So let me switch to that real quick. So yeah, decompose the following vectors into their x components and y components. Use the correct sign for the components. I forgot to elaborate on that last time. So my sign convention is that right is positive and left is negative for the x-axis, and up is positive while up is positive while down is negative for the y-axis. There we go. I can barely talk today. So yeah, with this exercise, basically the whole point of this is to just really get used to looking at your vector and recognizing what you'll get from multiplying its magnitude by cosine versus sine. Which components you're getting. Are you getting the opposite component or the adjacent component, and which one is in the x and which one is in the y? Basically, if these three weren't enough to really get you to just kind of quickly look at a vector and go 35 cosine 25, 35 sine 25, done. If these three examples weren't enough for that, then you can just draw more random vectors like this and just assign random angles to them and practice that until it starts becoming second nature to you, and until it becomes this sort of automatic, no thinking required sort of ordeal. Because you're going to be playing with vectors like this a lot, and if you have to get stuck and carefully draw your triangles every single time and write, your SOHCAHTOA every single time and do your cross multiplication, that's going to slow you down. And other than that, we have find the sum of the vectors in the following diagram. So we've got a diagram with 4 vectors that need to be added up. Okay, so for A, B, and C, we can go through that pretty quickly. Let me switch back to my camera. Gotta remember to do that. And let's have a look. So we had a 35 Newton vector at 25 degrees. I've already drawn the angle way too high, but let's pretend that this is a 25 degree angle. Okay, so instantly I go 35 cosine gives me the component touching the angle, 35 sine gives me the component across from the angle. So this would be 35 sine of 25 degrees. This would be 35 cosine of 25 degrees. And then that will give me their magnitude, and then I have to look at their direction. So this one's up, which is considered positive for the y-axis. This one's to the right, which is considered positive for the x-axis. So both positive values, and the rest is just work for your calculator. I don't think you need to see me go through that. Well, I'll plug in the numbers just to see. 35 sine of 25, I'm getting 14.79, give or take. And 35 cosine of 25, I'm getting 31.72. I'm getting 31.72. And those are in units of newtons. At the very least, this serves as an opportunity for you to also check your calculator settings and make sure you're in degree mode and not radian mode. So I guess there is some purpose in seeing what numbers I'm getting. And parts B and C are pretty much the same. If I flash back to B real quick, the twist with B is that the angle is given with the vertical. It's 28 newtons and it's 57 degrees with the vertical direction. So that might screw people up. A common mistake I see way too many students making is they will always associate cosine with the x direction and sine with the y direction. I think I talked about this last time, but it doesn't hurt to reiterate that cosine is associated with the adjacent direction, not necessarily x or y, and sine is associated with the opposite direction, again, not necessarily x or y. So that was 57 degrees and 28 newtons in length, and clearly not consistent with the other drawings, not on the same scale. Otherwise I would have drawn this a lot shorter. Well, not a lot shorter, but a bit shorter than this. About 80% as long. Anyway, components are going to be down and to the right, because that's just the way the vector is actually pointing. So we would have 28 sine of 57, opposite side to the 57 degree angle is this. So now sine is giving us the x component. Is that even? Yeah, it's still visible on the camera. So 28 sine of 57 this time is the x component. And we've got 28 cosine is going to be the y component. And because the y component is pointing downwards, I will associate that with a negative direction. 57 degrees. Okay, so 28 sine 57 gets me about 23.48 newtons, and 28 cosine of 57 gives me 15.25 if I round it. 15.25 newtons. I don't know why I chose to go with newtons. Well, probably because it has a very easy symbol of n, but you could use any type of vector here. It could be velocity or I was about to say torque, but I'm struggling to picture in my mind a scenario in which you would add actual torque vectors directly. Usually when we add and subtract torques, well, we'll worry about that when we get to the chapter that talks about torque. I'm overthinking things. Anyway, let's move on to... I'm going to skip C because I think the two examples we've shown are enough. Probably the first example was enough for most of you. And let's take a look at number 2. So I'm going to copy that diagram and then we can get started. Oh, and I'm just realizing I forgot to prepare paper. Give me a minute. Actually, is my... Oh, never mind. I have paper right here. It was just under another stack. All right. False alarm. Thought I was going to have to go to the other room to grab more paper. Actually, I mean, no, I'm going to need more space. I'm going to need more space for all this. So let's go ahead and see what I can do here. Copy that diagram. first and foremost, let me actually grab my ruler so that I don't screw this up. Watch me still screw it up somehow. And let me actually draw it a little bit higher. Yeah, there we go. That's a little bit better. Oh. I guess this pen is not feeling very cooperative today. That's a bit too long, probably. And something like this. There we go. Okay, that's about as nice as it's going to look. So our diagram has a green vector. I think I have all these colors among my pens. Yes, I do. Perfect. So I've got my green vector is 38 in magnitude, and then it's at a 19-degree angle. So, and that's the longest one. So the longer I make it, the longer I can make the other ones too, which isn't a bad idea, because then you can show things a little bit more clearly if you can afford to draw them bigger. Of course, at some point you have to compromise because you don't want to make it so big it takes up the whole paper. Okay, so that's green, and then for blue we've got 22 at a 67-degree angle with the negative y-axis. So something like this. And it was 22, which is a little more than half this length. Let's see. Yeah, a little more than something like that. I don't know why I'm bothering to be this precise with the lengths, but we're committed. And then we've got 30 newtons at 49 degrees with the negative x-axis. So 49 degrees, that's a little more than 45 degrees, so almost halfway. So halfway would be something like that. So a little bit higher, say something like this. Yeah, there we go. And then 30 newtons, so it definitely has to be longer than this, about 3/4 the length of this. I think I drew it too long. Let's see, that length. Yeah, I should have cut it off around, I want to say like here. Okay, and that's 49 degrees. And finally, we have our purple vector at 17 newtons. And it's going to be almost exactly half of this. A little less. Almost exactly half the length of the green, so something like that. 17 newtons. All right, so how do we work with this one? And I should actually just keep my pens with their tips sticking out instead of clicking them back in, since I'm using them so much. Anyway, so I want to, let's see, last time I showed how to do it using a chart. I think this time I just want to draw. Well, we'll do both. We can do drawing and charts. Okay, let's make a chart. So I'm just going to call the green one vector A, the blue one vector B, the orange one vector C, and the purple one vector D. And we're going to have let's see, I guess I'm going to call it vector AX for the X component of vector A. And AY for the Y component of vector A, and then BX, CX, DX, and then I'll have one extra line for the sum of those four. And for the Y components, I'll do the same. Oh goodness, why are my pens acting out today? There we go. I mean, at least they're faring better than when markers give out. When markers start dying out, there's pretty much no saving them. But with pens, if you scribble a little bit, especially if you can see that there's still ink in them, that's an advantage that pens have over markers. I can't see how much ink is left in this thing, for example. Yeah. Those are, I guess, two saving graces, is that you can actually see if there's still ink in there, and if you move it enough, you can usually get the ink to start flowing again with pens. Anyway, components, and I'm just going to use positives and negatives here for the X and Y direction, so I'm going to say positive X is this way, positive Y is this way, negative Y is that way, and negative X is that way. You don't need to use sign conventions if you don't want to. And I mean, they're a good tool for beginners when you're just working in situations where there are clearly two directions, a forward direction and a backward direction. It works great, but then for these two-dimensional vectors that we are originally breaking up, there is no sign convention that you can use here. Instead of signs, we just use angles, and there's an infinite number of possible angles that a vector could be directed at. It's not just every whole number degree from 0 to 360, it's also all the decimals in between them, literally infinite. So positive and negative, it's okay to use as a beginner, but eventually you want to just get into the mindset of thinking magnitude angle and have that be sufficient for you. Anyway, components. So I want to do the X component of this 38 Newton vector would be 38 times cosine of 19. The adjacent side to the 19 is on the positive x-axis, so that's going to be a positive value. And I'm going to do 38 cosine 19 gives me 35.93. 35.93. Give or take. if I do 38 sine of 19, then I'm getting 12.37, and that's in the upward direction, so that's positive 12.37. Okay, next up is my blue vector over here, so it's going to have, and I should actually just draw these components as I go. I should actually draw them. So this 38 is made up of a part that points up, like that, and a part that points to the right, like that. Of course, I could have drawn the part pointing up. I could have drawn it over here, and that's perfectly fine. Vectors don't really care where you draw them because vectors don't have like a physical location that they have to be at. I can freely move this thing here or here between these 2 points, or actually I could draw it anywhere I wanted, but you probably want to draw your vectors either connected tail to tail like this or tail to tip. I think the tail to tail drawing is a little bit better in this case because we're going to be adding all of these vectors, and it's nice to have all the verticals grouped up on the vertical axis while having all the horizontals grouped up on the horizontal axis. So that's why I'm going to be drawing the components tail to tail for this. But yeah, second vector, it's going to have a component pointing to the right like that, and it's going to have a component pointing down like that. So for its rightward component, we've got, well, this, if you moved it to here, it would be opposite of the 67-degree angle, so it would be associated with sine. 22 sine of 67 degrees, which is giving me about 20.25, so that's in the positive x direction, positive 20.25. And then in the y direction, if I do 22 cosine, by the way, definitely take advantage of the copy feature of your calculator if it has one. If you can just scroll up to expressions you've written before, highlight them, press enter to copy them over, and then go back and change whatever needs changing. Very useful for things that need to be calculated twice but slightly changed. Definitely a good idea to get to know your calculator. Anyway, I'm getting 8.596, which rounds up to 8.60 if I'm sticking to 2 decimals, and it's downward, so I'm going to write negative 8.60 over here. All right, next up is orange, so let me move this calculator out of the way and see if I can draw the components on this thing. We've got a component facing straight down like that, and we've got a component straight to the left like that. And if my drawing is correct, it should be less than 17 in length, but I guess we're about to find out. So the component to the left is, if I were to move this downward component and draw it here, it would make a right triangle where the downward component is opposite to the 49 degrees and the leftward component is adjacent. So we've got cosine for the left. We have, and I forgot to copy over its length, didn't I? 30 newtons. I forgot to write that down. I'm just realizing it now. Well, there you go. There's no escape from making mistakes, but there is the next best thing, which is catching your mistakes before you turn in your final answer. That's the actual area of improvement that you want to focus on if you tend to make a lot of mistakes. good practices to reduce your risk of making mistakes, yes, but also just developing the good habit of staying organized and just kind of checking every once in a while to detect any mistakes that may have been made. Anyway, 30 cosine, whoops, I typed 30 twice. 30 cosine of 49 degrees gives me 19.681, which rounds to 19.68, and it's to the left, so that's going to be negative 19.68. Okay, and then for the sine component, 30 times sine of 49 is 22.64. And that's straight down, so that's also a negative direction, so negative 22.64. And now that I'm looking at these numbers, I see that actually my original length for this orange vector may have been the better one, because this leftward component should have been longer than 17. Oh well. So much for drawing to scale. And finally, the easiest one is we've got 17 newtons to the left, so for the x component, I'll just write negative 17. And for the y component, well, there is no y component. It's 0. Okay, so if you are assigning positives and negatives as you went along, then all you have to do is just directly add these, because the ones that need to be subtracted already have a negative on them. If you did not do that, if you didn't assign positives and negatives, then you would look at these numbers and one by one decide, what do I add, what do I subtract based on which direction they're pointing. So I've got add 35.93, that green component is pointing to the right, plus 20.25 also to the right, and then minus 19.68 to the left, and also minus 17. And that should give us something that's overall to the right, I think. 35.93 plus 20.25. Oh yeah, those numbers are way bigger than the subtracted numbers. Minus 17. Okay, and I'm getting exactly 19.5. That's quite something. Did I type that all in right? 35.93 plus 20.25 minus 19.68 minus 17. Yeah, exactly positive 19.5. The fact that it came out positive tells me that overall it's to the right. Okay, now let's do the same thing for the vertical components. So I've got 12.37 up, negative 8.6 downward, and also negative 22.64 downward. Well, saying negative and downward is kind of a double negation. I want to avoid using that kind of language. I'll just say 8.6 down and 22.64 down. Yeah, that's probably the better way of saying it. And then a 0. So we've got 12.37 minus 8.6 and minus 22.64, and I'm getting negative 18.87. Negative 18.87. And this is another advantage to just assigning positives and negatives to your directions. It eliminates the need to predict whether the sum is going to be upward versus downward, or in the case of this first set, right versus left. You'll just get the sign to tell you which side wins out. So overall, it looks like we've got more down than up, and yeah, I can see that in my drawing actually. So if you were not assigning positives and negatives here, you would just have to look at your diagram and realize, yeah, I've got my total down is greater than my total up, and you would just do down minus up and get 18.87 without the negative sign, but you would note that it's downward and you'd be done. Anyway, we can now add these two components using triangle rule, Pythagorean theorem, however you want to describe it. What color do I want to use? Let's use red for this. So I'm going to draw that. I'm going to draw 19.5 to the right because that's essentially what it is. The positive doesn't necessarily mean having a positive value. It's just our convention for right. So that's 19.5 to the right and 18.87 downward. So, actually I probably should have written the 19.5 above the arrow for this, but I wasn't thinking. And then 18.87, almost the same length downward. And if I draw the right triangle, closing this, I get something like that. And its length is going to be a little more than 19.5, obviously, but not by that much, I don't think. Well, hold on. It's going to be something in the 20s for sure. So 19.5 squared plus 18.87 squared. Note that I've dropped the negatives from my drawing over here because, again, these signs really, the only thing they are is shorthand for the direction. And I get 736.3269. If I take the square root of that, I'm getting about 27.135, so that's going to round up to 27.14. About 27.14, and the units were newtons this time. Probably should have gone with no units at all, but I suppose this is good for practicing the habit of remembering your units, because you stand to lose a lot of points if you forget to include the units on your final answer, and that's not good. And as for direction, it's going to be approximately 45 degrees, what with these two being almost the same length. It's a little less, it looks like, and this is the angle that I'm looking for. So if I do inverse tangent of opposite over adjacent, opposite to this angle would be the 18.87, and touching it, adjacent to it, is the 19.5. 18.87 over 19.5 gives me about 44.059 degrees. So I'm going to round that to 44.1. This angle over here is 44.1 degrees. Or, final answer, to write it all fancy, 27.14 newtons at 44.1 degrees. If you look at that, that is below the rightward direction. So I'm going to say 44.1 below positive x axis, or positive x direction if you prefer. And that would be the final answer I would give to that problem. Okay. Now let's have a look at the next part of the assignment. Let me switch over. So what did we have? Vector addition with scalar multiplication and displacement. Okay, so just all of them. What do we have here? Number 1 is just more practice decomposing vectors, I think. Oh, no. There's more to it than that. Given vectors A, B, C, and D below, Part A, draw the following vectors by connecting vectors tail to tip. Draw carefully. No calculator work is necessary for this step. So just the drawing part of it. And we've got, 4 different sums. I think I'm just going to do one of them and call it a day for that one. And then part B says calculate the magnitude and angle made with the horizontal direction of the vectors you drew in part A. So draw them first and then calculate the sum. First part, no calculator required. Second part, use the calculator. Okay, let's go ahead and do that. So which one do I want? I think I will do this one. Actually, no, wait, let me do one that has subtraction in it. Yeah, let's do number 2. Let's do the second one. Let's calculate vector f. Well, let's draw it first and then calculate it. It's equal to 3b minus 2d. Okay, switch back to document camera, and let's see what we can do. I'm going to wall off all this. Oh my goodness. Why? Why must you betray me, pens? I should probably test out my pens before starting stream from now on. That's okay. I guess that's part of the fun of streaming. All of the surprising and unanticipated things that can happen. I'm sure some people live for that. I keep wanting to readjust the angle of my paper. I should really get something really sturdy to put on this table to just kind of block this from rotating, but I don't know if I have such an object at home that would also be small enough to still fit on this table, because this table isn't all that big. But we'll see, maybe I'll figure something out by next week. Anyway, we wanted vectors B and D, so vector B, I'm going to draw a copy of it. It's 46 meters per second, so it looks like we're working with velocity vectors here at 78 degrees to the right of the negative y direction. So we've got 78 degrees, something like that. I'm not going to bother drawing them to scale this time. 78 degrees, that's vector B. 46 meters per second. I do want to at least get the angles. Actually, you know what? Drawing them to scale is actually kind of important here, so I'll try my best. And then vector C, no, vector D is the other one here. So we want vector D, which is the purple one, 27 degrees above the positive x direction. So it looks something like this. 27 degrees. And it's 38 meters per second. So it's almost the same length as this one. Actually, let me use my ruler for this. How long is this? About 1.25 inches, so I'll draw this to be about 1 inch. That should be close enough. And that's vector D, which has a magnitude of 38 meters per second. Okay. And we wanted to draw vector F. Vector F, I will use, let's use dark blue for this. Vector F is supposed to be equal to 3b minus 2d. 3b minus 2d. Or another way you can think of this in your head is 3b plus negative 2d. That would probably be the better way of thinking about it. Okay, so I want to draw the vector 3b, so I'm going to draw something about 3 times the length of b and in the same direction. I need to find a place for these pens. Hold on. Yeah, let's put them over there. They're probably going to get in the way of my mouse later when I try to shift between pages on my screen, but we'll deal with that problem when we get to it. We had about 1.25 inches, and I want to draw 3 of that, so try to keep the same angle, and let's draw over here. Okay, that's about 1, and then that should be about 2, and then that should be about 3 of B. That should be 3B. So there's 3B. I'm hoping I actually have enough space here, but something tells me I don't. Minus 2D, minus 2D. So I'm gonna try and keep this same angle. I don't even know if this angle is right. And its length was supposed to be about 1 inch. So minus 2D, 2 times the length of D, but in the opposite direction. So, oh, just barely. It does look like it will fit. Yeah, there we go. So that's negative 2D. And I've drawn them tail to tip, so I can now just take that exposed tail, connect it to that exposed tip, and I have my sum. What color was I using for F? Yeah, this dark blue. And actually, let me use the ruler for this so that I don't screw it up too badly. Aren't you glad that we have the calculator method of finding vector sums and we'll never have to do this again? That's almost a right triangle. Almost. Actually, it very well might be. Hold on. Let me check real quick. If that's 27 degrees there, then this would be 27 degrees here, and if this is 78, then this would be 90 minus 78 is 12. Oh, no, it's not. Hold on. That would be 12 degrees. 12 plus 27 would be 39. Yeah, I'm not sure. It does look like a right triangle, though, so we'll see. We'll check the math and see whether or not they make right angles to each other later. If that does turn out to be the case, then that is pure coincidence. I never, when I wrote these problems, I never intended for this to be the outcome, but it very well could be. Anyway, so now we've actually drawn the vector F. It's going to look something like this, if my scale is accurate enough. 3b minus 2d. And part B is asking us to actually calculate it now. So we didn't do an example with scalar multiplication last time for a vector sum, but I imagine you can already guess what it's going to look like. I don't think this will trouble most of you. You just break the vectors into components and you multiply the components of b by 3 and you multiply the components of d by 2 or negative 2 depending on how you're doing your sign conventions. So I can say, another way of saying this is, you can say that the x component of f is equal to 3 times the x component of b minus 2 times the x component of d, and the y component of f, the vertical component of f, is 3 times the vertical component of b minus 2 times the vertical component of d. And let's go ahead and actually draw those components. So where are my colors? I've got light blue is there, purple is there. Okay, so B has a component to the right like this and a component downward like this. This time I'm not going to use signs. And D has components to the right and up. Okay, so for B, the component touching the 78 degrees, the cosine component is down, so that's the vertical component. By is going to be 46 times cosine of 78, since it's touching the 78. And this is going to be, wrong color, 9.56 is what I'm getting. If you want to call it negative 9.56, be my guest, but I want to do an example where we don't use that. And then for the horizontal component, I'm going to do 46 times sine of 78 degrees. And my calculator says 44.994, so 44.99. 44.99 meters per second. And I should probably be calling these bx and by. Okay, and for vector d, we are going to have the side touching 27, so 38 cosine of 27 degrees is 33.858, so I'll round that to 33.86 meters per second. That's for the x component of d, so that's dx. And for the y component of d, that's going to be opposite to the 27 degree angle, so 38 sine of 27 degrees gives me 17.251, so 17.25 if I round to 2 decimal places. And for those of you who aren't sure how I'm deciding how to round, I'm just rounding to 2 decimal places. I'm not worried about sig fig rules. I went over that little spiel in last week's stream, so you can go check that if you want my reasoning behind it. But bottom line is, save your sig fig rules for AP chemistry, because in AP physics, unless your teacher is really nitpicky about it, the AP physics exam itself doesn't really care. As long as it's reasonable, you're fine. 1, 2, or maybe 3 decimals when you feel like it's necessary is good enough. So don't get too hung up on sig figs. They understand that you're students and that sig figs aren't something that you need to be bogged down by until you're actually working for NASA. As I like to tell my students, worry about the sig figs if you're actually working on the billion-dollar rockets for NASA, because then, getting your calculations exactly right is of utmost importance. Lives and a lot of money are at risk But this is just, you're just learning, so I wouldn't get too fixated on sig figs unless you are, again, in AP Chemistry, because it's a little bit more important there. Okay, where was I before I went off on my tangent about sig figs? I guess you don't have to go back to the previous stream for that spiel, because I unintentionally ended up reiterating the same thing here. And now I'm trying to figure out where I was. Okay, so we got the components, and now we can use those to get the components of f, which we can then recombine using Pythagorean theorem to finally get the overall magnitude and direction of f. Okay, so 3bx minus 2dx for the x component of f. Let me switch to this color. So let's see, 3bx, so 3 of 44.99 to the right minus 2 of 33.86 to the right. Well, if I'm subtracting right, then that's the same as adding left. And so if I've got, I'm going to have 3 times 44.99. So we've got 3 of, I'll draw it this time as 44.99 right minus 2 of 33.86 right. I know this notation is kind of informal, but I'm trying to get you to think in 2 different ways for how to do vector addition and subtraction, because having more than one way to look at things can usually kind of open up your mind to new possibilities. If you get too stuck on one convention, then that just sets you up for failure as soon as you're exposed to somebody who does things differently from you, even though they're actually trying to arrive at the same result as you. And yeah, that's no good. There's usually more than one way to get things done, and being able to understand when somebody is doing things differently from you is important. Okay, so we've got 3 of this to the right minus 2 of this to the right, so you could also rewrite this as 3 of 44.99 to the right plus 2 of 33.86 to the left. And now we've got 3 times 44.99 is 134.97, and then 2 times 33.86 is 67.72. And now I see, since one of these is to the right and the other is to the left, the one to the right is bigger, so I'm going to do bigger minus smaller. And since the bigger one is to the right, the overall result is to the right. So I get, well, let's subtract them. 134.97 minus 67.72 gives me 67.25 to the right. Let me wall this off. Equals 67.25 to the right, or positive x direction, if you will. Okay, what about Fy? So Fy, we've got 3 times By is 9.56 down. And minus, well, I'll skip that part. I'll switch it to a plus immediately. And then 2, and then dy. dy is 17.25 up, but since there was a minus in front of it, I'll switch it to down. So it's plus 2 times 17.25 down. Okay, so now I've got down plus down, which is overall down, so I'm just going to add these directly. So I'm going to do 3 times 9.56 is 28.68, and 2 times 17.25 is 34.5 on the dot. And if I add those numbers together, then I will get, whoops, almost highlighted the wrong thing there. Well, actually, what I had highlighted would have given us the same result. And we get 63.18 downward. I get 63.18 downward. And I forgot the units, didn't I? Meters per second. Meters per second. Down, downward, however you want to say it. Okay, and now, moment of truth. Right and down are my components, and that makes sense. My drawing says that F is supposed to point right and down, so we are in agreement there. That's one way to check that we haven't made any silly mistakes. And if I do some Pythagorean theorem, well, I guess I can try to draw what I've got. So this is going to be my fx right here. Whoops. No, wait, I drew it way too long. What am I doing? I should have stopped all the way over here. Yeah, fx is about that long, and fy is just going to be this. 67.25 and 63.18. Yeah, I guess my drawing is off because this is supposed to be longer than this. Oh well, at least I tried. Okay, now I'm more confident that this was not a right triangle we were making here. Anyway, if I want to figure out this angle, the angle made with the horizontal, then I can just do opposite is the vertical component over adjacent is the horizontal. So we would do 63.18 over 67.25 equals tan theta. Inverse tan of 63.18 over, where was it, 67.25. And I'm getting about 43.2 degrees. I'm getting 43.2 degrees. And so I would say F is equal to, I didn't get the magnitude yet, did I? No, I did not. Well, let's do Pythagorean theorem now. 67.25 squared plus 63.18 squared is 8,514.2749. If we take the square root of that, we get 92.2728. So 92.27. 92.27 meters per second. And it was at, I don't know why I used a comma there, at, I guess you could use a comma, 43.2 degrees below positive x direction, or positive x-axis, whatever you prefer to call it. I think I did both. Yeah, last time I called it axis. And there we go. Is that visible on the screen? Yes, it is. Gotta keep checking for that. Maybe if I was checking for that before, I wouldn't have had the mishap where you guys were staring at the PDF screen while I was drawing triangles and parallelograms. Anyway, next up, wait, wasn't there something else I wanted to do here? Actually, yeah, there is one more thing before we move on to the next question. So, I'm sure for a lot of people it's kind of intuitive that, when you get a vector by adding multiples of other vectors or subtracting, as the case may be, then it makes sense that you would do the same thing with their components, but maybe you're not entirely sold on that idea. Maybe some of you still don't entirely believe that, or you do believe it, but you want something that counts as more of a proof. So what I'm going to do is just take one of these vectors, b or d. Let's do b, and let's take a look. Well, actually, maybe I'll just draw a brand new vector. Yeah, I'll do orange, and I'll use that little bit of unused space over there for it. So if I have a vector, let's call this vector, what do I want to call it? Let's call it q. Let's say I have vector q that looks like this. And let's say this, actually this angle doesn't even matter. Let's just call it theta. And let's suppose we've got the two components for it, which are going to be qx over here, and the other component is qy. If I multiply the vector q by a number, then I necessarily multiply the components of vector q by that number. If I were to draw another vector, let's say 2q, because that's probably the most I'm going to be able to fit in here. So draw something parallel to this. Okay, so that's about 1q, and then that's about 2q. Okay, so now I have the vector 2q. It's at the same angle. They're drawn parallel to each other, so same angle theta over here. And through triangle similarity, since I've got this angle theta is the same between them and they both have the same right angle, that's two angles, and we know that if a triangle has two angles in common with another triangle, then those triangles are similar. If I know that these two triangles are similar, then I know that the ratio of length from here to here equals the ratio of length from here to here and from here to here. So I know that whatever this is, since the hypotenuse of 2q is twice the hypotenuse of 1q, then I know that this horizontal side must be twice the length of qx, and this vertical side must be twice the length of qy. And that follows for any other number you put in here. If you made this 3q, then it would follow that this is 3qx and 3qy, and so on and so forth. So if you weren't completely sold on it, or you just had some hesitation as to how to prove it, there you go. It's really just triangle similarity. When you multiply a vector by a scalar, you are multiplying all of its components by that same scalar. If a vector can be thought of as a sum of two components, then multiplying a vector by a number just means distributing that number over that sum, over the two components that you add to make that vector. Okay, now we can move on to the next part, which says use the diagram below to answer the following questions. So we've got a diagram, we've got a little bit of a number line game going on here, and we have somebody moving to different points along this number line. So part A is asking, what is the distance covered by someone who travels from point A to point G, then to point F, then finally to point E. So distance is the key word there. What is the distance covered by someone who travels in this way? And then part B says, what's the distance covered, again, by someone who travels from D to E to B to A, and then finally to H. And then part C is asking, what are the displacements of the two people in parts A and B? Are they the same, and should they be the same? Why or why not? So if you did this, then you should have noticed the twist. So let's take a look at this. I don't think I need to switch back to my document camera for this. We can just do it by looking at the screen. So I have, starting at point A, they move to point G, so from -4 to -7, so they move 1, 2, 3 steps. Then to F, they move, let's see, from -7 all the way to 2. That's 9 steps, right? 7 steps to 0 plus 2 more. So I've got 3 plus 9, so that's 12 so far. And then to E. So from F to E, I'm going 1, 2, 3, 4 steps. So that's in addition to the 12 I already did, so that's 16. I'm going to write the 16 down. So for part A, I'm getting 16 steps in terms of total distance. Okay, part B. What is the distance covered by someone who travels from point D, over here, to point E? So from 6 to -2, that's 8 steps. Then to point B, that's 1 step from E, so 8 plus 1, 9. And from point B, they go to point A, so 9, and then 10, 11, 12 to get to point A, so that's 12. And then finally to point H, from -4 to 8, that's 12 more, so wait, I lost count. Oh, I should have been writing as I went. Okay, from D to E is 8, 9, 12, plus 12, okay, 24. So part B, I'm getting 24. Let's write that down as well. And then part C, what are the displacements of the people in parts A and B? Okay, so part A, they started at point A, they ended at point E. Displacement is the change in position, where you are minus where you were, between two specific times of interest. In this case, the time when you were at position E and the time you were at position A. Well, not you, but you know what I mean. So it looks like position E is 2 steps to the right of A. So overall, even though they kind of moved around back and forth, in the end, what they ultimately achieved is that they ended up 2 spaces to the right of where they started. They ended up 2 spaces to the right of where they started, so their displacement is 2 steps right. I'm writing this down, even though you can't see it. 2 steps to the right. And then for the person in part B who started at point D and ended at point H. So they started here, they moved back and forth and around, and in the end they got to point H. They also ended up, in the end, 8 minus 6, 2 steps to the right of where they started. So they also had a displacement of 2 steps to the right. Are they the same? Yes, they are. Should they be the same? Some people might have a misunderstanding about this because they think, well, person A went from point A to point E, person B went from point D to point H. So even though they both ultimately ended up 2 steps to the right of where they started, did they achieve the same displacement? Yes, they did. Remember what I said earlier about how vectors are not physically attached to some physical location in space. Displacement it doesn't have some sort of fixed location attached to it. All it is by how much and in what direction did the position of something change. We have two things, or in this case, two people, that both ended up 2 steps to the right of where they started. They had the same amount of change to whatever their starting position was, and that change was in the same direction for both of them. Their displacements are the same. Their initial and final positions are not. Position is what you're thinking about, not displacement. Their displacement, their change in position, the amount and direction of it are the same. So yeah, they're the same, and they should be the same. And now we move on to number 3, which is basically just a 2-dimensional displacement question. I think this one I'm going to just copy over on paper and follow along. So let's switch back to the camera and let's see if I can recreate this. I guess I don't need all that anymore. I just wrote it down for myself, really, so don't need that anymore. That's from the previous problem. Let's do, I want my black pen, which is right here. Wait, is that the, hold on. These two colors are too close to each other, even under good light. Okay, yeah. Black versus navy blue, they look almost the same. They look almost the same. At least to me they do. I wish they would have done something to make them a little bit easier to tell apart. I don't know. Can you guys see the difference between these two? Because they are different. This one's black, this one's navy blue. Anyway, let's draw a coordinate system, and this one, I want to make it actually pretty big. I traced over it like 4 times, and still nothing. Okay, let's try. That's a little bit better. Okay, there we go. That's about as good as I'm gonna get it. And then something like that. Okay. We can work with this. It looks like the footage in the preview window on YouTube Studio is looking kind of blurry. I hope that's just on my end and that you guys can actually just adjust it to 720p on your end. I hope. If not, then that's something I forgot to do for last week. I need to look at the recording for last week and see, well, not the what do you call it? I guess the VOD from last week, and see if YouTube actually saved it at the same quality that it was streamed at, because if not, then I'm going to have to just upload the recording that I did. Anyway, those worries aside, I want to go ahead and draw, let's see, how many spaces do I need? I guess I should have drawn it a little bit more biased to the right. Yeah, let's stretch this out some more. And see what we can do. So I need, well, up to 8 spaces to the right let's see, I'll just use, centimeters work. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then to the left, I just need 3, but I'll do 5. 1, 2, 3, 4, 5. Okay, vertically I need about 5 up and only 1 down. Maybe I should have prepared this ahead of time, but it's fine. It's not like I'm in any rush. It's not like I have a preset time for these sessions. I mean, I would like them to stay between like 2 to 3 hours, give or take. I think that's a reasonable amount of time for a physics lecture. Well, might not be reasonable to some of you, but considering the pace I want to go at and considering that I want to be done somewhere past winter break at the latest, I think 2 to 3 hours is reasonable enough. Anyway, let's mark these 1, 2, 3. I should have just counted by 2s. 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. -1, 2, 3, 4. And -1, 2, 3, 4, 5. Hopefully I didn't write over a location where I have to draw one of my dots. Okay, so it says for part A, what is the distance traveled by someone who travels from point A to point I, then to point H, then to point D, and then finally to point B? I think I'll just use the same color for all of these points. So A is here. G is over here. I'm just going to draw them as I see them rather than alphabetical order, which I'm probably going to regret. 4, 1 is I. And then 3 steps to the right of that, 7, 1 is H. And then it looks like D is 4 steps above and 1 to the right of that. So 1 to the right and 4 above, so it's at 5, 8, something like that, so that's D. And then B is at 2, 5. So there's B. And C is 2 steps above I. I think I drew that slightly off, a bit too far to the left. Okay, C. And then E and F are all the way back there, so F, -3, 1. And E is 3 spaces above that, so 2, 3, 4. And there's E. Okay, what is the distance traveled by someone who travels from point A to point I, then to point H, then to point D, then finally to point B? So their travel looks something like... Actually, wait, let me read the other ones first before I draw over this diagram. And then the other person goes C to I to F to E to G. There's 1 point in common between those two routes, so I think I'm good. Yeah, I'm good. Okay, so from A to I, maybe I should use my ruler for this so I don't screw it up. So they go from A to I. And then to H, and then to D. There we go. And then from D to B. Should be a straight horizontal line if I drew my points in the right places. Yeah, what is that distance? And then we'll deal with the other distance in a minute. So this is actually not too hard to do. You just draw a bunch of right triangles and do Pythagorean theorem to figure out the lengths. It's just basic coordinate geometry. If you remember from your geometry class, the distance formula, the square root of x2 minus x1 squared plus y2 minus y1 squared. That's essentially what you're doing here. You're going to have a bunch of square roots. I'm just going to keep things written with square roots and not have decimals in the mix. Well, we'll probably convert everything to decimals in the end. So from here to here, we've got 4 to the right and then 1 up. So that's going to be the square root of 4 squared plus 1 squared. That's the square root of 16 plus 1, square root of 17. From I to H, that one is easy enough. That's just 3 steps. From H to D, we've got 1, and then we've got 4, so that's square root of 17 again. And then we've got from D to B is all the way from 8 to 2, so that's just gonna be 6. Okay, 3 plus 6 is 9, so 9 plus 2 root 17. Part A, 9 plus 2 square root of 17, and you can plug this into a calculator if you want to condense it all down to a single number. So that's part A. Part B, what is the displacement of this person? Give the magnitude and angle made with the horizontal direction. So displacement, I would just draw a straight line from A to B. Magnitude is the length of that line. Direction is whatever angle this is. It'll be a right triangle. You can just drop a vertical from there, and that's your right triangle, and do Pythagorean theorem and inverse tan. We've done all that before, so I think I will skip that part unless it becomes relevant later. Part C, what's the distance traveled by someone who goes from point C to I to F to E to G? C, I, F, E, G. C, I, F, E, G. C, I, F, E, G. Let's do purple for this. C, I, F, E, and where is G? G is all the way down there. Okay, so C to I is just 2. I to F is from 4 to -3, that's 7. F to E is just a distance of 3, and then E to G, we're going from -3, 4 to +2, -1. So from -3 to +2, that's 5 horizontally. And from 4 to -1, that's 5 vertically. So 5 squared plus 5 squared is 50, so square root 50. Square root of 50. Did I do that right? -3 to 2 is 5, and 4 to -1 is also 5. Yeah. Okay, so overall it's 2 plus 7 plus 3, so 12 plus square root of 50. So part C, 12 plus square root of 50 would be the total distance, which again you can plug into a calculator if you really want to condense it down to a single number. And then part D, what is the displacement of the person in part C? So displacement in going from, they started at C, they ended at G, so their displacement looks like this. And again, I can just drop a vertical and make a right triangle there and figure out my magnitude and direction. I can do Pythagorean theorem between, let's see, from a height of 3 down to -1, so that's 4, and then from 2 horizontal to 4 horizontal, that's 2, so 2 squared plus 4 squared, 4 and 16, so that's square root of 20, and then I guess I would use this angle and use that for the direction. I guess you could also use this angle. Well, actually no, I think I would rather use this angle because the overall direction of the displacement from C to G is in this direction, down and to the left, so I would probably want an angle that's actually touching. Yeah, I think I would rather use this as my angle, although I guess you could also draw this as an angle made with the horizontal instead, so you've got choices. But I'm going to skip over that because I think we've done enough of that for today. Part E, what is the displacement from point F to point B? I think we've already done enough of that, so we'll skip displacement from B to C. And from F to... Oh, okay. This one might actually matter. Hold on. So they've got F to B, and then B to C and F to C. F to B. This is starting to get rather crowded, but F to B. And then they've got B to C. And then they're asking for part G, what is the displacement from F to C? And I'll use a different color for that. Let's use, I guess I haven't used my dark blue in a while. Actually, let me use green for this. I think that will stand out among all these other colors. What is the displacement from F to C? And what you would notice if you did some vector addition here, part H is asking what is the displacement obtained from the vector addition of the displacements that you found in parts E and F, and how is it related to the displacement you found in part G? So you would just get whatever this displacement is, whatever you get for it, you would probably just decompose it back into, what is it, from f to b, it would have a component of, from -3 to 2, it would have a component of 5 to the right and 4 up. And then this displacement from b to c would have a component of 2 to the right and 2 down. And you would add those components and get an overall displacement of 7 to the right and 2 up, which is the same as the displacement from f to c. So f to b plus b to c equals f to c in terms of displacement. Yeah, that was the point that I was trying to get at with this assignment. If you move in a bunch of steps, then you can calculate the displacements between those different steps and then combine them to get your total displacement, and that total displacement will always be the same as what you get if you just directly calculate from the first step to the last step. Just basic vector addition at work, but knowing this gives you the advantage of knowing that you don't have to actually decompose those two vectors in order to find their sums. You can just calculate the displacement directly from f to c, which can sometimes be helpful. It can sometimes save you time. Okay, now we delve into the math essentials for physics. Let me switch to this tab. Okay, so I've got my little blurb over there, which you can read if you want to. Basically, it's just like the underlying philosophy for why I even created this document in the first place and why it's important to do some math practice before you do physics. There's a lot of math in physics, and if you are too rusty with your math, you're going to have trouble. Because in physics, the math is sometimes going to be a lot more, perhaps creative isn't the right word, but loose with the rules isn't the right thing to say either. It's not so much it's loose with the rules, it's more like you have to think outside of the box a little bit compared to what they teach you in your algebra class. In your algebra class, they teach you how to solve systems of linear equations, but they don't really teach you much beyond that. In physics, you're going to find yourself having to sometimes solve systems of one linear equation and one non-linear equation, or two non-linear equations. Like you might have to solve two quadratic equations with each other or something like that. So just practicing some of these habits that they don't really make you develop in your traditional algebra course is important. So first one says, solve the following equations for the indicated variable or variable expression. And by the way, there's more than one way to solve most of these. There's more than one path to a solution. So let me switch back over to here and let's see what we can do with these. And also I might as well check the time. How long have I been going? Almost 2 hours. Okay, we're good. I think we have enough time to finish up the math essentials, and then I'll see if I can come up with an idea for what to cover after physics, and if I don't have anything, then I guess we'll call it a day. But yeah, I guess we will be postponing one-dimensional motion until next week after all. So solve. First we've got 2x plus y squared, 2x plus y squared equals 3x over y. Okay, a couple of different solution approaches you might come up with, some more efficient than others. So part of the fun in this is see if after solving it one way, see if you can discover another way and see if you can discover what's the most efficient way for you. And by efficient, I don't always mean the fewest number of steps. Sometimes you have solutions that involve less steps, but the steps are more complicated and harder to follow, and it's very easy to make mistakes. So that's something you need to take into consideration as well. It might be efficient on paper in terms of not having to write as many lines, but it might not be so mentally efficient. So those are things to consider. So this one said solve for x. So we need to get the x by itself. So what a lot of my students tend to do for this first one is they don't like seeing this y in the denominator, so they multiply everything by y, and they get 2xy plus y cubed equals 3x. Then the next step would be to group the x terms together, so I would subtract 2xy, so that would give me y cubed equals 3x minus 2xy, and then factor out the x, so you get y cubed equals 3 minus 2y all times x. I can check my work. If I distribute the x over these, then I do get back 3x minus 2xy. And then divide by 3 minus 2y, and you get x equals y cubed over 3 minus 2y. Okay, that's one solution. Another solution is to just go ahead and group the x terms as they are. You can, when you see 3x over y, you can also see it as 3 over y times x. You can just view the 3 over y as being a coefficient of x. So another approach would be to just go ahead and subtract 2x on both sides, and you're left with y squared equals, I'll write it as 3 over y, x minus 2x, and then factor out an x. So we get y squared equals 3 over y minus 2 all times x. And divide by 3 over y minus 2, and you get y squared over 3 over y minus 2 is equal to x. I probably should have written that equal sign a little bit lower. Yeah, something like that. And this is another solution, and this one only took 2 steps. So we've got 1, 2, 3, 4 steps versus, well, I guess 3. 1, 2, 3 steps. Now you might be saying, well, wait a minute, these two don't look the same. How are they the same? You can now take an extra step to clean it up and just multiply the top and bottom by y. Multiply by y over here and multiply by y over here, which distributes over the bottom since the bottom has multiple terms. And that would get you, well, y times y squared gives you y cubed over y times 3 over y is just 3 minus, that'll be 2y, and there you go. So it is the same result. Now, whether you want it written this way or this way, I suppose it depends on what you are trying to discover, what you're trying to prove with your physics problem, but we don't have a physics problem associated with this one, so I guess wait until you see a scenario that kind of looks like this. And then you get to make the call as to whether this or this is the better format. But yeah, what I was describing earlier, this is more efficient on paper because it's taking fewer steps, but this one might be easier to grapple with mentally. If you don't like dealing with fractions, then it's definitely a great idea most of the time to just multiply by the common denominator across the whole equation and get rid of all the fractions that way. What's the term? Clearing the fractions is what I've seen in some textbooks. I think that's what they call it, clearing the fractions. Okay, next one. And I guess I'm going to need a new page for this. Have I already? Yeah, that's already on the back side of another paper, so let's grab a new one. Next one says we've got 5x squared plus 8y over 3x minus 2y equals x cubed. Solve for y. 5x squared plus 8y over 3x minus 2y equals x cubed. Solve for y. We need to solve this for y. Okay, so I'm basically going to set it up kind of like what I had over here, where you're just going to have a bunch of terms on the right side and a bunch of terms on the left side, and then I'm going to group together any terms that contain the variable I want to isolate and group them all on one side of the equation and throw everything else onto the left and then factor. So that's the technique for both this one and the previous one. Group and factor. Group and factor. Remember it, because you'll be seeing situations where you need to use that in physics. You'll definitely see that. Okay, so I'm going to go ahead and multiply 3x minus 2y across to the right-hand side. So that will give me 5x squared plus 8y equals x cubed times 3x minus 2y. Your instinct might be to go ahead and distribute this, and usually that will help get you somewhere, and I think in this case we're actually going to want to do that. But there are cases where you may not want to do that, so be careful about that. In fact, one of the solution paths for this one involves, instead of distributing, you could divide the x cubed over to the left-hand side instead. And I guess I will show that after using the distribution version. So I would get 5x squared plus 8y. If I distribute the x cubed, that's 3x to the fourth minus 2x cubed y. Then I want to group the y terms together and group the x terms together, so I'll add 2x cubed y to the left and subtract 5x squared to the right. You could do the opposite. You could subtract 8y to the right and subtract 3x to the 4 to the left. Either way, you will get equivalent answers, and it might be worthwhile to actually look at both answers and be able to recognize at a glance that they are equivalent. Because if this was like a multiple choice, for example, and you had to choose the right expression and you solved one way, and then the answer choice that they wrote down looked different from what you had but was equivalent to it, you would want to be able to recognize that. So let's go ahead and try both routes. Let's try first the route I described. The reason I prefer it is because the thing that I want to factor the y out of would become positive if I add 2x cubed y to the left. So if I do 2x cubed y plus 8y equals, I subtracted 5x squared, so that's 3x to the fourth minus 5x squared. And then from there, factor out the y. You've got 2x cubed plus 8 all times y equals 3x to the fourth minus 5x squared. Divide, and you get y equals 3x to the fourth minus 5x squared over 2x cubed plus 8. Okay, and if I did the other route with this, I guess I will use, let's do the navy blue. Which one's, yeah, this one's the navy blue. If I do it the other way around, where I group the y's onto the right, then that would be 5x squared minus 3x to the 4 equals, if I subtract the 8y, then I get negative 8y minus 2x cubed y. Factor out the y, we get 5x squared minus 3x to the fourth equals negative 8 minus 2x cubed all times y. Divide, and you get y equals 5x squared minus 3x to the fourth all over negative 8 minus 2x cubed. And you might look at these and go, well, they don't look the same, but they actually are, because this one is just 5x squared minus 3x to the fourth is the negative of 3x to the fourth minus 5x squared. So whenever you flip the order of subtraction, that's something a lot of people forget. You are just getting the negative of something. If I do 12 minus 7 versus 7 minus 12, those are the same magnitude, but opposite direction, I guess you could say. One is negative, the other is positive, but their distance from each other is, well, not from each other, their distance from 0 is the same. Their absolute value is the same. So remember that. Reversing the order of subtraction is the same as applying a negative sign. And if I look at the negative 8 minus 2x cubed, well, I've got two minuses. I can factor those out into a negative, so there you go. I've got a negative in the bottom that was distributed over these two terms, and I've got a negative in the top because I've flipped the order of subtraction compared to what I have over here in purple. So yeah, with enough practice, you should be able to quickly recognize that these two things are the same. If you solve your problem like this and then the answer choices on the multiple choice look like this, you should be able to quickly recognize that this matches what you got over here. Okay, then there was one more solution path we can take. At least one more. There's probably even more than that. I've had students who will take steps that they eventually end up undoing. Like they'll distribute something only to then factor it out a few steps later. And that's something you want to watch out for while doing these. You'll probably catch yourself doing stuff like that, adding something only to subtract it later, or multiplying something only to divide it later, or vice versa. That's part of the goal of the Math Essentials, is to get you to catch yourself making these mistakes and realize ahead of time when you're about to make them so that you can save yourself time and stress and all that good stuff. Anyway, I was going to do non-distribution with no distribution. If I divide x cubed over to the left-hand side, then I get something like 5x squared over x cubed just becomes 5 over x, plus I'm just going to call it 8 over x cubed y equals, and then 3x minus 2y. And from here you can go two different routes, kind of like what we did over here. You can go two different ways. I'm just going to pick one of them. I'm going to pick basically the same thing I did over here. I'm going to add the 2y because I like making my target positive, and subtract the 5 over x. So I end up with 2y plus 8 over x cubed y equals 3x, and then subtract 5 over x to the right. Factor out the y. And we get 2y, or no, wait, not 2y, just 2, plus 8 over x cubed, all times y equals 3x minus 5 over x, divide, and now you have a very complicated looking expression, 3x minus 5 over x divided by 2 plus 8 over x cubed. And if you multiplied the top and bottom of this complex fraction by x cubed and you distributed it, then you would end up with basically this. So this is not the cleanest answer, but it is an answer. And does it take more steps than the others? Hold on. Oh, no, it only looks that way because, okay, we've got 1, 2, and then 3, 4, 5 steps to a solution there versus 1, 2, 3, 4, 5. Okay, so all of them are 5 steps, but this one is definitely the most headache-inducing. So try to avoid this. If you practice these problems enough, you'll be able to see this coming from a mile away, and then you can just go and take the detour and go pick one of the less headache-inducing solution paths instead. Unless, of course, like I said earlier, there might be merit in writing it this way. It really depends on the problem and what you're trying to show or prove. Maybe this would be better in cases where you're trying to show that when x gets really, really big, y approaches the value of 3x over 2, because when x is really, really big, you're taking this 5 divided by a big number, which becomes really small, and same thing, 8 over a really big number becomes small, and so these two terms might become negligible if you had some sort of physics problem where this x or whatever physics concept it's representing becomes too big. Then you might see some sort of special behavior that you're trying to prove. Actually, we see more of that in electricity and magnetism than mechanics, at least based off of the examples that are coming to mind for me right now. But I feel like there should be something in mechanics. It just eludes me right now, but there are definitely scenarios in mechanics where we make some sort of simplification based on a value being really large compared to another value. Anyway, next up we've got This trips up students a lot. I think I will do it up here. We have m squared over p equals 1 over n squared plus 1 over m. M squared over p equals 1 over n squared plus 1 over m. So one thing a lot of students do wrong here is they will try to flip all the terms. They will try to incorrectly, I'll do this in red, they will incorrectly say p over m squared equals n squared plus m. Absolutely wrong. Absolutely wrong. I can immediately disprove this. I mean, you could do, for example, 1/2 is equal to 1/3 plus 1/6. Does it follow then that 2 equals 3 plus 6? No, not at all. So if you ever feel like you might be doing something that's not allowed mathematically, just test it on some real numbers and see. Of course, I guess it depends on what numbers you test, because if you test on 1s and 2s and 0s, you might get a coincidental special case. So you might want to try and prove your ideas with numbers that are uncommon and not likely to produce some sort of weird special case. But anyway, so if you want to flip both sides, then you actually have to flip both sides. Flip the left side equals flip the right side, the whole right side. So what you can do, so let me actually continue down here. What you can do is you can say p over m squared equals 1 over the whole right side, 1 over n squared plus 1 over m. This is something you could do. And the other thing you could do is just multiply throughout by n squared. In fact, what some students will do is multiply by the common denominator of all three of these fractions. They'll multiply by mpn squared, or pn squared m, however you want to say it, whatever order. The order doesn't matter for multiplication. But yeah, if you do it this way, then now what you have to do is find a common denominator between n squared and m. So I would just multiply by m over m here, and multiply by n squared over n squared here. And that would get me m plus n squared over n squared m. So that would be, I guess I'll switch back to red here. I get p over m squared equals 1 over m plus n squared over mn squared, which can be rewritten as just mn squared over m plus n squared. This doesn't look like it's bringing us any closer to a solution. We're trying to get the n by itself, and now it looks like we've created a situation where we have n's in multiple locations. So maybe not the most efficient solution, but it is a solution, so let's keep going with it. If I then multiply the m plus n squared over to the left-hand side, then I get p over m squared times m plus n squared equals mn squared. And instead of distributing and making this even more of a headache, I'm just going to multiply both sides by m squared over p. And that will get me m plus n squared equals, this is going to become, if I multiply by m squared over p, that's becoming m cubed over p times n squared, and subtract the n squared over to the right hand side, and now you've got m equals m cubed over p n squared minus n squared, factor out the n squared, and divide, we have m equals m cubed over p minus 1 all times n squared, and divide by m cubed over p minus 1 and take the square root, and there's your n. Which square root, positive or negative? In this case, because we don't have any context, we have to list both. We have to say plus or minus the square root. So where do I want to write this? I guess I've got a little bit of space left over here. Let me actually switch colors so that it doesn't blend in with everything else I did. So I will, let's see, divide by m cubed over p minus 1, so m over m cubed over p minus 1 equals n squared, so plus or minus the square root of m over m cubed over p minus 1 is equal to n. I don't know if it's the positive or negative root. We will often have situations in physics where we know from the physics for sure whether it's the positive root or the negative root. So unless you have the physics to confirm whether it's going to be the positive or the negative, when you take square roots, just leave open the possibility of both signs. Very common mistake that physics students make is forgetting that the square root operation can give you a negative. Part of the reason we screw this up is because our calculators will never give you two answers. Calculators are programmed when I do square root of, I don't know, 25. It gives me 5. It doesn't give me 5 and negative 5. The human is supposed to recognize that negative 5 is a possibility. The same thing goes for the inverse trig functions. If you've done your pre-calculus, you know that sine of 30 degrees is 1/2, but you also know that sine of 150 degrees is 1/2. So when you do inverse sine of 1/2, it tells you 30, and the human is supposed to recognize that it actually means 30 or 150. But for the calculator, they have to simplify it and restrict and narrow down the possibilities to just one answer, because I guess the programming becomes more difficult if you allow the option of listing multiple answers. Although, would it be worthwhile to create a calculator that reports multiple answers? I don't know. Maybe somebody who actually works in the industry and produces calculators can comment on that, but I feel like it wouldn't be too hard, at least to write the code for it, but maybe something about designing the circuitry for it might make it more costly than it's worth. Yeah, that could be it. Or maybe the calculator manufacturers are just lazy. Could be any of those possibilities. Okay, so this is one possible route to a solution. So we did what? 1, 2, 3, 4, 5, 6, 7, 8 steps. We can probably do better than that. If nothing else, we can probably find something that's less headache-inducing than all of this. So let's see if we can find that. New page. M squared over P equals 1 over n squared plus 1 over m was the original statement. And one of the things that I pointed out while trying the previous solution was we had a situation where we were trying to isolate n squared and we ended up just kind of spreading it over multiple places, which made our job a little bit harder. So let's see if we can avoid that this time. Let's try and subtract 1 over m. So I get m squared over p minus 1 over m equals 1 over n squared. Oh, and now if I take the reciprocal of both sides, I get 1 over m squared over p minus 1 over m equals n squared over 1, or 1 over n squared, which reduces to n squared. Okay, and I could just say I'm done here, take the square root and be done with it. That is an option. We can just go plus or minus square root of very ugly looking complex fraction. We can do this, but chances are you're going to want to try and simplify this left-hand side a little bit more before you go that route. So I can do the same thing I did before, just find a common denominator, which would be m times p. So multiply this by m over m, multiply this by p over p. So we get 1 over m cubed over pm minus, that's just going to be p over pm, or mp, however you want to write it, equals n squared. And then from there we can write pm over m cubed minus p equals n squared, and then we can square root n equals plus or minus the square root of pm over m cubed minus p. Okay, so if we assume this longer route where we actually bother to simplify, we've got 1, 2, 3, 4, 5 steps as compared to, what did we have before? 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Clever choices can save you time and headache. At least one or the other. And if you're lucky, both. So yeah, I believe this is the most optimal route. But if you're trying to optimize for headaches, maybe you don't like how both of these routes involved writing complex fractions. Maybe you don't like either of those and you're willing to take more steps just to avoid headache. Then you can do what I was hinting at earlier. Multiply by, let's see, I would multiply by mn squared over here. And multiply by mp over here. Wait. No. I'm overthinking it. multiply everything by p n squared m. So you get p n squared m times m squared over p just becomes n squared m times the original m squared equals p n squared m times 1 over n squared is just pm plus, and then 1 over m times p n squared m is just pn squared. And then, well, this simplifies to n squared m cubed. I wouldn't really count that as a full step. Maybe I would count that as a half step. Equals pm plus pn squared. And then group the n squared terms. So subtract the p n squared over to the left. N squared m cubed minus p n squared equals pm. And then factor out the n squared. And divide pm, mp, whatever, m cubed minus p. Yeah, there we go. And then square root, and you get n equals plus or minus square root of mp over m cubed minus p. So how many steps is that? 1, 2, 3, 4, 5, 6. A little bit longer. Not as long as the very first method we tried, but a little bit longer than this more efficient route that we took. But a lot less headache-inducing, as long as you're very, very careful with that first step of multiplying everything by p n squared m. All right, let's take a look at another one. H equals fk over g squared. We've got a lot of room in the middle here. H equals fk over g squared plus 2k. H equals fk over g squared plus 2k. And it says solve for k, then solve for g. Solve for k, then solve for g. Okay, solving for k is pretty easy. We've done enough of this at this point that you should know what to do. The k terms are already grouped. Factor out the k and divide and you're done. Factor out k, so we've got h equals f over g squared plus 2 whole thing times k. Divide what's in the parentheses over to the left, and you get k equals h over f over g squared plus 2. And you're done in 2 steps for that one. The other thing they said was solve for g. Solve for g. So I could try to solve for g from here, or from here, or from the start. It looks like it would be easiest to do if we just go ahead and take care of it from the start. So I'm going to do something similar to what I did up here, where I'm going to isolate the fk over g squared. So I'm going to subtract 2k. So I'm going to subtract 2k and get h minus 2k equals fk over g squared. Take the reciprocal of both sides. So that becomes g squared over fk equals 1 over the whole thing, 1 over h minus 2k. and then multiply by fk and take a square root and we're done. G squared equals fk over h minus 2k, and square root gives us, I guess I'll write it over here so that I have space for the next problem here. G equals, I was about to write a plus, G equals plus or minus square root of fk over h minus 2k. And there we go. I guess I could try to divide the top and bottom by k. I don't think that would help much. We'd eliminate k from the top, and in the bottom this would just become h over k minus 2. I don't know if that helps at all, but it is an option that you should consider in case, again, you were doing this as part of some sort of multiple choice question and you got this far and none of the answer choices looked like this. If you saw something that had an h over k in it, then dividing top and bottom of this by k would be the way to get to that. But that's pretty much it for that one. Nothing too remarkable about it, considering what we've seen before. We're just kind of using the techniques we've learned from the previous ones to get through this one more efficiently. Next one says k squared equals j squared plus 4fg. And it says solve for j, then solve for f. So let's draw a divider there. And let's go for this color now. K squared equals, I'll write it over here. K squared equals j squared plus 4fg. I think this one is modeled after the third equation of kinematics, if I'm not mistaken. In case you were wondering, some of these I just kind of made up on the fly, while others are actually based on equations that you see in physics, but I changed the names of the variables, so yeah, now you know. Solve for j, then solve for f. I mean, this one seems simple enough. Subtract 4fg and take plus or minus the square root, and there's j. And solving for f, subtract j squared and divide by 4g. Okay, that one's actually not that hard. We'll skip it. 1 over a squared equals 1 over b plus 1 over c. Okay, yeah, we'll skip this one. And we've got the next one is 1 over a squared, 1 over a squared equals 1 over b plus 1 over c. And it says solve for a, then solve for b squared. Solving for a is pretty much the same process as what we had here. Once you got to this step where you isolated 1 over n squared, solving for a is pretty much the same exact steps from this point onward. So we will skip on solving for a. Solving for b squared is the more interesting part, because now, the first time in this set, we're solving for not just a single variable, but we are solving for an expression involving a variable. Sometimes you have to do that. Sometimes you have to solve for an expression. Sometimes you have to solve for a square or a ratio of two variables or something like that. So that is the new twist here, but otherwise nothing too difficult. If we are solving for b squared, then I guess we need to solve for b first. So I would subtract 1 over c. So let's start up here and write 1 over a squared minus 1 over c equals 1 over b. And I think this time what I'm going to do is find a common denominator and simplify the left before I flip both sides. There's no reason why I have to do it after. If I already see it coming, it might look nicer if I do it like this first instead of ending up with this sort of mess. So multiply by c over c here and multiply by a squared over a squared there, and we get c over a squared c minus a squared. So c minus a squared over a squared c equals 1 over b. And then flip both sides, and we get a squared over c minus a squared equals b. And if we're solving for b squared, all we have to do now is square both sides, and we get a to the fourth times c over c minus a squared quantity squared equals b squared. Whether or not you should FOIL this into c squared minus 2a squared c plus a to the fourth really depends on what it is you're trying to do in your physics problem. It might be better to just leave it like this in the parentheses instead. So there may be one extra step here depending on whether or not it is worthwhile for you to FOIL. All right. Next one says, can I actually do it with the last remaining line on this page, or do I need a fresh new page? What color have I not used in a while? Let's do orange. 1 over v squared equals wv minus w over u. It says solve for u, which is not too bad, and then solve for square root of 1 over w. Yeah, this needs a new page. Do I want to do that first one? I mean, it's not too different from the ones we've already done that had fractions in them. It's not too different. The only thing is there's a w in there, which I could factor out. I could factor it out to simplify. So let's do 1 over v squared, copy it over first, equals wv minus w over u. And solve for u. Let's go ahead and actually do that. So one thing I could do is divide the w over to the left-hand side. And that would end up with me having 1 over wv squared equals v minus 1 over u. But do I want to do that? I mean, I have to get rid of the w that was, I had to get rid of it eventually, so might as well get rid of it now and confine it to one place, is my thinking. But I feel like I might be undoing that later. At least that's what my instincts are telling me. Anyway, next up, we're probably going to want to isolate this 1 over u. So we could subtract the v over to the left, or we can add 1 over u and subtract 1 over wv squared, which is more steps because you're doing 2 steps instead of 1, but at least you get rid of the negative in front of the thing that we're trying to solve for, so I think it's worth it. Plus, also it shows you this little quick trick. You're basically having these swap places. You're subtracting 1 over wv squared from the left and adding 1 over u to the from the right to the left, so you end up with 1 over u equals v minus 1 over wv squared. Yeah, this sort of quick swap trick, if you look at enough cases where you do this, then eventually it just becomes second nature to you, some really quick algebraic manipulation that you can do. You could do it in 2 steps, but with enough practice you can just do it all at once. Okay, and then this I can rewrite as wv cubed over wv squared. So 1 over u equals wv cubed over wv squared minus 1 over wv squared. So wv cubed minus 1 all over wv squared. Does that simplify to v minus 1 over wv squared? Yes, it does. Okay, and then flip, and you end up with u equals wv squared over wv cubed minus 1. Okay, that wasn't too bad. And then the other thing it asked us for is solve for the square root of 1 over w. Solve for the square root of 1 over w. Where do I want to start? I think I actually want to start from here, because here I've already got my 1 over w. I just need to get rid of the v squared and square root, and then I'm done. So actually, let's start from here. So multiply by v squared on both sides, and I get 1 over w equals v squared times v is v cubed minus, that's just going to become v squared over u, and then square root of 1 over w. Okay, yeah, we're already done. So from here to here, and from here to square root of 1 over w equals plus or minus the square root of v cubed minus v squared over u. All done. Let me draw that v a little bit bigger so that the 3 doesn't eclipse it. Okay, and we're done. We don't need the plus or minus on both sides because that would just be redundant. Yeah, we don't need the plus or minus on both sides. Okay, next up is r over s cubed equals t to the 4th minus 16 over r squared. Solve for t, then solve for s over r. Whoops, didn't mean to draw over that, but should still be readable anyway. If you were copying that down, just rewind a couple seconds if it's become unreadable. And copy down, the next one is r over s cubed. R over s cubed. Oh, now the ink is flowing a little too much. Equals t to the 4th minus 16. You might be tempted to do difference of squares here because you see t to the 4th and 16. I don't think that's needed here, but if you caught that, that's good, because there will be opportunities where you actually do want to catch that and recognize that it's a possibility. Anyway, solve for t, then solve for s over r. So we're looking for t, and we're looking for s over r. Let's do t first. So not too hard, actually. Just multiply the r squared over to the left. And that gives you r cubed over s cubed equals t to the fourth minus 16. Add 16 and take the fourth root. R cubed over s cubed plus 16. Whoops. Let me do plus 16 on this side. Arrow, and then, yeah, and an arrow here, and an arrow there. Equals t to the fourth, and then t is simply plus or minus, because it's an even-powered root, plus or minus the fourth root of 16 plus r cubed over s cubed. Okay, that one wasn't too bad. Fairly straightforward. And then solve for s over r. Solving for s over r. I could start from the very beginning, or I could start from one of these steps, if it happens to be convenient. And I think this over here might actually be the most convenient starting point, because I've got r cubed over s cubed, which I can cube root to get r over s, which I can then take the reciprocal of to get s over r. I don't even have to follow that order. I could take the reciprocal first, which I think I'm going to do. So I'm going to write s cubed over r cubed equals 1 over t to the fourth minus 16. And then cube root both sides. Cube roots do not need the plus or minus. So then I get s over r equals the cube root of 1 over t to the fourth minus 16. Yeah, cube roots do not require the plus or minus. The cube root of a negative is always a negative. The cube root of a positive is always a positive. There's no guesswork there. Okay, that one wasn't too bad. Next we have d over 12 minus c squared equals ab over c squared, and it says solve for d over b and solve for c. What color? Let's use this one. We've got d over 12 minus c quantity squared equals ab over c squared. Like I said earlier, you might be tempted to try and FOIL this. That might not be the best of ideas. First it says solve for d over b. Solve for the ratio of d over b. Okay, I can just multiply by 12 minus c quantity squared over to the right and divide the b over to the left, and I'm done. So yeah, let's do that. So we've got d equals ab 12 minus c squared over c squared, and then divide by b, and I've got d over b. Actually, let me write it over here. D over b a times 12 minus c quantity squared over c squared, and leave it at that. 2 steps and done. It says also solve for c. Well, my c is in 2 places. It's inside this 12 minus c thing, and it's also over here. And it looks like I might want to actually just continue from what I have here to solve for my c. So you might think, and this is a possible solution, you might think that foiling the 12 minus c over here, squaring this out, and then cross-multiplying and then grouping all of the c terms is a good strategy, except you're going to end up with a mix of c and c squared terms, which are going to be hard to then gather back into one term. So the actual strategy here, and you'll see equations that look like this in the gravitation chapter, the actual better strategy here is to hold off on foiling the expression in parentheses until you can actually eliminate the squares altogether. So what I'm going to do is I'm going to divide by a, and that's going to get me to d over ab equals 12 minus c squared over c squared. I should probably draw a dividing line between those just so those don't get mixed with each other when rereading it later. And now what I can do is I can square root both sides. Now I can just square root both sides of this equation, and that will result in, I'll do it over here. I guess I'll draw an arrow. Square root of d over ab. I guess it would be plus or minus the square root. Wait, do I need the plus or minus here? I'll just put it in just to be safe. Equals 12 minus c over c. Well, I guess it depends on the sign of c what the square root will be, because if c is less than 12, then square root of d over ab would have to be positive. If c is greater than 12, it has to be negative. So the plus or minus sign, I guess it wouldn't actually be necessary, because whatever 12 minus c over c turns out to be would dictate whether it's a positive or a negative. But I'll keep it for now, and if I realize later that having this is a problem, then I will point that out. Anyway, now we can multiply the c over to the left-hand side. And that gives me plus or minus d over ab multiplied by c equals 12 minus c. And add a c to the left, and that gives us c plus or minus square root of d over ab times c equals 12. Factor out a c. And we get c equals z equals 12 over 1 plus or minus the square root of d over ab. And in the actual physics situation where this problem took inspiration from, I'm pretty sure that only the positive root would be a possibility, but without the physics context, I think this plus or minus is necessary. I'll have to think about it more later on, and if I realize that we can actually eliminate one of those two possible signs, then I will either comment on it in the next stream or post a pinned comment or something. Okay, next up, the last one from this first set. We have z equals 4 pi square root x over y minus 8 quantity squared. And it says solve for x over z squared, then solve for y. What color do I want to use? I feel like I haven't used green in a while. So z equals, this should be from the simple harmonic motion chapter, is the equation that inspired this one, just based on how it looks. 4 pi square root of x over the square of y minus 8. I was about to say 1 there. Solve for x over z squared and then solve for y. Okay. Well, if it's asking me to solve for x over z squared, then clearly I need to square the z. So let's go ahead and actually square both sides of this, and that will give me z squared equals 4 squared is 16 times pi squared is pi squared times all the stuff under the square root squared just gets rid of the square root, and that leaves me with x over y minus 8 squared. I guess I don't really need those big parentheses, but just for clarity's sake, I will include them. And if I want x over z squared, I can also just do z squared over x and then flip it. That's probably the safer way to go about this. It's not as messy as trying to divide the z squared over to here and move everything else to the left. So I'm going to do z squared over x equals 16 pi squared times 1 over y minus 8 quantity squared. I'll just move the 16 pi squared into the numerator of y minus 8 squared, so 16 pi squared over the square of y minus 8. And flip, and we're done. At least with the first part. X over z squared equals y minus 8 quantity squared over 16 pi squared. Okay, then it says solve for y. It says solve for y after this. Actually, I think I want to just continue from here to solve for y. I think I want to just continue from here. So all I have to do is square root both sides, which feels like a redundant step because we started off by squaring both sides and now we're square rooting. Actually, let me look. If we started from the beginning, I could rewrite this as square root of x over y minus 8. Yeah, I guess we could do that. That is another avenue. that we could pursue, but it just looks so much easier starting from here compared to here. It just looks so much easier because we already have the y in the numerator. That's already a good thing. And square rooting both sides isn't too difficult starting from this. So yeah, since we've already done this work, I don't feel like it would be a waste to continue from here. But if it was only asking you to solve for y from the very beginning, then yeah, I guess you could just start from here, flip both sides, and yeah, you could start off with 1 over z equals 1 over 4 pi times 1 over that square root. So that just becomes square root of y minus 8 squared, which is y minus 8, over square root of x. And then take this 4 pi square root of x and multiply it over to the left and add 8, and you're done. Yeah, that's one route you could go, definitely. 4 pi root x over z equals y minus 8. And I guess there would have to be a, well, no, we don't need a plus or minus here because it wasn't included in the beginning. Yeah, we don't need a plus or minus in front of the square root there. And then add 8, and you've got y. So okay, I guess it's not that bad doing it from the start. 4 pi root x over z plus 8 equals y. What if I did it from here? I would square root both sides, which would give me root x over z. I guess since I'm the one introducing the square root, that would add some plus or minus business, which I know I don't need because of this. Okay, yeah, this is actually the better route. Now that I'm looking at it, this was way easier than I expected. Okay, never mind. This is just undoing work that we already did over here, which is retracing steps and wasting time. All right, that was the first problem. And I see we are past the 3-hour mark. Maybe I should save problem 2 for next time then. Well, no, I'm gonna finish it off. It'll probably be another half hour, which I am fine with. Oh, don't need a new sheet just yet. Still getting used to the idea that pens allow me to use the backside of a piece of paper. Okay, let's have a look at the second set. I might as well put them up on screen for a minute. So second set says solve the following systems of equations for the indicated variable or variable expression. And you see a bunch of systems of equations that are definitely not linear systems of equations. This one and this one are of great importance. This one is a bit, I didn't think far enough ahead while making this one and realized too late that it's a bit simpler than I intended for it to be, while this one was a little bit more complicated than I intended for it to be. But yeah, let's go through them and see what we can discover. So some of these have actual numerical solutions, while others are just going to have some sort of expression. And in physics, you're going to see a lot of these sort of expression problems where you have to derive an expression for something and not necessarily solve for a number. So that's something to get used to. First one is 2x squared plus 5xy plus y squared equals 16. 2x squared plus 5xy plus y squared equals 16, and x plus y equals 3. And it says solve for x and y. And in this case, we are going to get actual numerical answers. So a lot of times in physics, most of the time when you're working with multiple equations, the go-to tactic is substitution. There are some rare cases where elimination might be the way to go, but most of the time, substitution is your go-to method. So I'm going to take this second equation over here and rewrite it as, let's do y. Let's do y equals 3 minus x. It really doesn't matter which one you pick. And then I'm going to plug that in. I'm going to substitute that for y in here. So that gives me 2x squared plus 5x times 3 minus x plus 3 minus x squared equals 16. And if I distribute and simplify, I get 2x squared plus 15x minus 5x squared plus, that's going to be 9 minus 6x plus x squared, all equals 16. If I group together my x squared, I get 2 minus 5 plus 1, so negative 3 and plus 1 is negative 2 x squared, and then 15x and negative 6x is plus 9x, and then I've got the plus 9 over there equals 16. I'm going to move everything over to the right hand side because then that gets rid of the negative. I very much prefer working with a positive coefficient on my x squared if I'm going to be working with quadratics. So 0 equals 2x squared minus 9x, and then subtracting 9 from 16 is plus 7. Okay, can I just factor this? 1 and 7, yeah, 1 times 2 plus 7 times 1. Well, it factors into, they're going to be minuses, so I'm going to have 2x and then minus 7 and x minus 1. Minus 7x minus 2x gives me minus 9x. Okay, and that leaves me with the possibilities that x equals 1 or x equals, let's see, if it was 7 over 2, that would become 7 minus 7 equals 0, so x equals 7 over 2. Those are my possibilities. Now if I test them out, I get either y equals, when x is equal to 1, y equals 2, so y equals 2 when x equals 1, or when x equals 7 over 2, or 3.5, y equals 3 minus 3.5, which is negative 1/2, or y equals negative 1/2. So you've got two possible solutions, 1 and 2, or 7/2 and negative 1/2. Those are your two possibilities. And I believe they both work if you plug in those pairs. So if I do 1 and 2, 2 times 1 squared plus 5, 1, 2, so that's 10, 2 and 10 is 12, plus 2 squared. 12 plus 4 is 16. That works. And then 7 halves and 1 half. I think I'd rather just use a calculator for this to save time. 2 times 3.5 squared plus 5 times 3.5 times negative 0.5 plus negative 0.5 squared. I'm getting 15.5 and not 16. I screwed up somewhere. Where did I mess up? 2 times 3.5 squared plus 5 times 3.5 times negative 1/2 plus, oh, I added the negative, I don't need that. Plus negative 1/2 squared is not the same as plus the square of negative 1/2. Okay, there we go, 16. Okay, so that was just a calculation error on my part. I plugged in my negative 0.5 squared wrong. Calculator tip while we're here. Negative 0.5 squared does not equal negative 0.5 in parentheses squared. Remember that when you are working with the square of a negative. If you're squaring a negative, just don't even bother writing the negative sign to begin with. That's the way to avoid the mistake I just made. And then you'll be good. Okay, next one says W sine theta equals 60 and W cosine theta equals 80. This should look somewhat familiar. Some of you might already see where this is going. W sine theta equals 60 and W cosine theta equals 80. Yeah, solving for unknown angles is a common thing that you didn't get to do in algebra. You barely did it in geometry when you learned basic trig. But in physics, it's a new ball game. Solving for unknown angles is not super common, but it is common enough that you're going to want to pay special attention to this type of problem. So there are two different ways to deal with this. One for those that are really in the know. You just kind of start learning to use this strategy through experience. And another way that's a little bit more, I guess you could say, back to basics, classic. So the classic method is just use substitution. So I will solve for W using one of these. I'll use the one on the right, for example. And I'll do W equals 80 over cosine of theta. And then I will substitute that into the first equation, which gives me 80 over cosine of theta times sine of theta equals 60. And you might be familiar with a trig identity that tells you that sine of theta divided by cosine theta is equal to tan of theta. In case you haven't heard of that before, maybe you jumped into AP Physics 1 without completing pre-calculus yet. Maybe you're in pre-calculus right now and you haven't gotten to the trigonometry portion of that course. Then you might not be familiar with it, but sine of theta over cosine of theta is equal to tangent of theta, and we can prove it quite easily. That if sine of theta is equal to opposite over the hypotenuse, and cosine of theta is equal to the adjacent over the hypotenuse, then I can just multiplied by hypotenuse over adjacent for the top and bottom of this expression. I can multiply by hypotenuse over adjacent here, and multiply by hypotenuse over adjacent here. And what do I get? Well, in the bottom it just completely cancels out. Hypotenuse times 1 over hypotenuse is gone, and adjacent times 1 over adjacent is gone. Over here, hypotenuse times 1 over hypotenuse is gone, and you're left with opposite over adjacent, which is tangent. So sine over cosine is equal to tangent. This is an important trig identity to remember. Sine over cosine equals tangent. Sine over cosine equals tangent. And so this simplifies. We get 80 tangent of theta equals 60. Divide by 80 on both sides. 60 over 80, or 3/4, is equal to tan theta. Tan theta equals 3/4, and now I can just use inverse tangent of 3/4 on my calculator. The key to solving for an unknown angle when it's stuck inside of a trig function is you want to try and merge all of your trig functions into one trig function, because then you can just use a sine inverse or a cosine inverse or a tangent inverse. But there is no inverse of something like sine times cosine or sine squared of an angle. So you really do need to, well, I suppose I could come up with an inverse sine squared process, maybe, though it would probably be ugly and not all that useful. I think that's something I'm going to have to think about later. Anyway, where was I? So inverse tan of 3 over 4 is about 36.9 degrees. That should look familiar. That should look quite familiar. Theta equals 36.9 degrees. 36.9 and 53.1. You are going to see a lot in physics because they're associated with one of the simplest right triangles you will ever see, the 3, 4, 5 triangle, or 6, 8, 10, if you will. If this is 4, and this is 3, and this is 5, and it's a right angle, then this angle is going to be 36.9 degrees, give or take, and that other angle is going to be 52.1, right? 36 plus 52, 80, no, it's 53. 36.9 and 53.1. You'll see that a lot. Sometimes you'll see this rounded to 37 degrees and 53 for the other one. But yeah, don't be too surprised when you see this specific triangle showing up over and over and over again through your practice problems. It's a very popular triangle. And for good reason. I mean, look at all these lengths. They're nice and round. No ugly decimals. Anyway, that's solving for theta. What about solving for w? Well, now that I know theta, I can just plug it into one of these and solve for w. So I could do w times sine of 36.9 equals 60. And if I did that, then I would get 60 divided by whatever my calculator says for sine of 36.9 would give me w equals approximately 100. But there is another way to do it without actually finding theta first. You can actually get w first. And the way to do that is to use yet another trig identity. So this is one trig identity. And another trig identity you can use is sine squared of theta plus cosine squared of theta is equal to 1. So let's prove it before we use it. Sine squared of theta, not to be confused with sine of theta squared. So let's talk about that real quick. Sine squared of theta does not mean sine of theta squared. You will see this in other types of functions, especially functions that are not polynomials, functions that are not expressions involving simple x's and y's and square roots and such. Whenever you have some sort of, what's the word I'm looking for? Some sort of like, I guess I would call it a nicknamed function because I can't think of what these functions would be called. I guess they would be called transcendental functions, but that probably doesn't mean anything to you. Whenever you have functions that, are like short words for something, and then they're applied to some sort of number, putting the square before the number that the function is supposed to be applied to means that you actually square after you plug in the number. So basically, sine squared theta, what it really means, sine squared of theta, what it actually means is you take sine of theta, and then whatever that is, you square it. Whatever that is, you square it after the fact. Another example would be the logarithmic functions. You've probably done logarithms in your algebra class. If I did something like log of, 100, and I wanted to then square that, I could write it as log of 100 and then squared, or I could also write it as log squared of 100. In general, if I have a function and I want to square it, if I want to square f of x, if I want to square it, then I would write f squared of the thing I want to apply the function to. And the order is you plug the thing into the function and then you square. The function squared of, we call this the argument. The function squared of the argument just means you apply the function to the argument first and then you square. So that's explaining the notation for those of you who haven't finished pre-calculus yet. Okay, so proving sine squared of theta plus cosine squared of theta equals 1. I'm going to go ahead and put this in a box so that I don't lose track of it, but it's not too hard to prove. If I have a right triangle, I guess I'll draw a separate one from this because this one already has numbers on it. Let's do it up here. If I have a right triangle, any right triangle, it doesn't matter what this angle theta over here is, this will be the opposite. Since it's not touching the angle, this will be the adjacent, and that will be the hypotenuse. Then sine squared plus cosine squared just means I'm squaring opposite over hypotenuse, so opposite over hypotenuse squared plus adjacent over hypotenuse squared. And if I go ahead and square the top and bottom, exponents distribute over multiplication and division. They don't distribute over addition and subtraction, but they do distribute over multiplication and division. Then I get opposite squared over hyp squared equals adjacent squared over hyp squared. They have the same denominator, so I can put them together. Opposite squared plus adjacent squared all over hypotenuse squared. That's what this becomes. But what's opposite squared plus adjacent squared? What's this side squared plus this side squared? Well, Pythagorean theorem tells us that it's equal to this side squared. It's equal to the hypotenuse squared. So this is just hypotenuse squared over hypotenuse squared, which of course is 1. Hyp squared over hyp squared, which equals 1. So there you go. That probably bored some of you out of your mind if you already had your pre-calculus, but for those who either didn't have pre-calculus or completely forgot it, now you know. This is another important trig identity that you need in physics. You're not going to use it every single time, but there will be occasions where you want to use this. These two are of utmost importance, and there are a couple of other identities that might be used in very rare scenarios that they probably wouldn't throw at you during the test, but I'll bring those up when the time comes for them. Anyway, so if I want to take advantage of this, I can just start from w sine theta equals 60 and w cosine theta equals 80. And what I can do is something that they definitely never taught you in algebra class. I can square both sides of both equations and add them to each other. And what does that achieve? Well, we're about to find out. If I do w squared sine squared of theta, so I'm just, the square of w sine theta is, well, w sine theta times w sine theta is w squared, and sine squared equals 60 squared, which is 3600. Or I could keep it as 60 squared, it doesn't really matter. W cosine theta equals 80. If I square that, then I get w squared cosine squared. Remember, exponents distribute over multiplication, so square of w times cosine is the same as square of w times the square of cosine, equals 80 squared, which is 6400. And now I can just add these equations to each other. Yeah, adding and subtracting equations is not just for solving equations by elimination. As you learned in algebra class, you can do more. You can add equations to each other whenever you want. It's just that usually you're not going to get anything useful out of it unless you've planned ahead for why you're adding or subtracting them. So if I go w squared sine squared plus w squared cosine squared, then 3600 plus 6400 is 100,000. Or no, not 100,000, 10,000, which is also 100 squared. And if I factor out the w squared, then I get w squared times sine squared of theta plus cosine squared of theta, which is, as we learned just a minute ago, which is 1. That equals 100 squared, is how I'm going to write the right-hand side. Okay, so this reduces to a simple 1, and now we're left with w squared equals 100 squared, w equals 100. And if you're wondering why I'm not doing plus or minus the square root here, it's because I know for sure this is positive 100. It has to be positive 100 times sine of 36.9 degrees is the only thing that can give me positive 60, and same thing for positive 100 times cosine of 36.9 is the only thing that can give me 80. Your calculator will give you some sort of decimal that easily rounds to 60 and 80, so if your calculator is disagreeing, it's just a slight difference because of rounding. But there you go. So that takes care of that one, and I see we've been going for 3.5 hours. Should I press on? You know what? I will leave the rest of this as homework for next week, and we'll start off next week by covering the remaining ones, or maybe I'll just record a separate video for that, and next time we will start looking at one-dimensional motion. I think this is a good place to just call it a day. 3.5 hours is plenty. So yeah, any announcements I want to make before I leave you for today? Let me think. I would recommend, so I guess let me switch to my computer screen over here. I would recommend that you go ahead and look at the reading sections and do the kinematics overview. What is this? Yeah, this was a video. The moving man simulation is an actual homework PDF, right? Yeah. Okay, let's actually do this. So let's do this one for homework. You can open this link. It's the moving man simulation. In case they change the link or anything like that, you know, in the future, if you're watching this like a couple years from now, just type PHET simulation moving man and Google should be able to find it for you. But yeah, play around with this simulation and see what you can learn about the concept of acceleration. And we will start things off by going over this next time. Well, I don't know if I want to start off with this. We'll see. I'll talk about like concepts and definitions, and maybe then we'll jump into this. And apart from that, looking at worked examples, we can hold off on that because I still need to show you guys like equations and formulas, unless of course you look at the kinematics overview and read the chapter sections and feel like you're ready to go ahead and do problems. Then you might want to look at the worked examples before trying the problems and exercises. But what I would recommend, if you're not ready for actual problems, is the conceptual questions. Maybe read them and start thinking about them at the very least. And yeah, that would be my advice in terms of preparation for next time. And that's it. So next time we will, unless I've already released a separate video for it, we will wrap up with the remaining parts of that Math Essentials set that we were on. We will look at those. And I will post links. I'm pretty sure I have solutions for section 3 and onward. I will post links to those videos in the description or the pinned comment, probably the description, once I get around to that. So hopefully by sometime tonight or tomorrow night, I will get that done. I will get around to it. I'll track down those links and post them, and maybe even put some timestamps on this and the previous stream recording. And yeah, we'll cover the rest of this if I don't release a video for it. And then we'll just start talking about motion in one dimension, going over definitions and all that stuff. And then going over the questions for this moving man simulation. And that'll be that. Study hard, keep practicing, and I will see you guys next week.